right. Well, good afternoon. Good morning, everyone. Welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Grabowski, and I'll be your host for today. As we have just passed the halfway point of October, we have had a ton of live action for classrooms. This is our space month. So we've been talking to astronauts and engineers and scientists who are making exploration beyond our planet possible, out into our solar system and beyond, looking at our universe, but then importantly, turning the lens back on Earth and allowing us to see and look at our planet in ways we never could before. So if you visit exploringbytheseat.com, you can find all the events we have coming up for the rest of October. We hope to see your classrooms joining us live. And then if you visit our YouTube channel, you can find all the live content from this month and back in the past. So you can tune into lessons that you may have missed. All right, let's get into today's space exploration action. Today, we're going to spend a little time. We've got Winston hanging out with us today, Winston Jackson. He is going to talk to us about Europa Clipper and its journey to Jupiter. So Winston began his career in systems engineering at NASA's Jet Propulsion Laboratory in 2014. He has worked on missions like helping to integrate, verify, and validate the science instruments of the Mars Perseverance Rover. He is currently he did serve as flight director and mission operations system engineer since the launch of Europa Clipper since 2024. He's also supporting the VERITAS mission to Venus. So he is a busy guy when it comes to space exploration. Let me see if I can reach backstage and find Winston. Here we go. Hey, Winston, how are you?
Hi, Joe. How are you?
Yeah, good, Winston. It's really great to have you joining us live today.
I'm happy to be here.
All right, excellent. Well, Winston, we've got classrooms joining us from Canada, from the United States, basically from across North America. We're going to turn them loose with questions eventually. But before we do that, we want to get to know you a little bit and dive into Europa Clipper. So we'll let you take over for a bit.
Yeah, thank you. Again, happy to be here and always excited to talk about the Europa Clipper mission. I'm just going to jump right into it. I'm a senior systems engineer at JPL, and I was one of the lead systems engineers for the Europa Clipper mission. I had the opportunity to be the systems engineer that worked to coordinate our mission once we arrived at Jupiter to study Europa. I'll start out by just talking a little bit about what Europa is. If you know Jupiter, you know that Jupiter has many, many moons. 4 of them are particularly special to the planetary science community: Callisto, Ganymede, Europa, and Io. I'm going to focus today on Europa because to us, Europa is the most special. It's one of the 4 largest Galilean satellites, and they're called that because Galileo discovered them back in the 1600s, just using kind of what we would consider rudimentary optics today in a telescope, where he saw these bright objects in the sky, and he was wondering what they were. Today, we know exactly what they are, but we don't know a lot about why they look the way they look and behave the way they behave. And so the Europa Clipper mission is one of the few missions following the original mission called Galileo to go and actually try to study Europa up close. And so there's a good reason for that, why we want to study Europa up close. Many scientists believe that Europa has the ingredients for life, or it could have the ingredients for life. And so why is that? It is one of what we call an icy moon in our solar system, where it is composed of a lot of water, much more water than all of Earth's oceans, for example. It has some essential elements that we know on Earth led to the formation of life, which we can talk about a little later. It has a chemical energy source that is really due to how Jupiter and Europa play together as it orbits around Jupiter, and Jupiter's strong magnetic field. It creates some hydrothermal energy, and so we can talk about that as well. And so it's been kind of what scientists call simmering in this state for about 4 billion years. And so it's a very exciting scientific place to go explore more closely. I'm going to talk to you next about something pretty near and dear to me. 1 year ago, as of October 14th of this year, 1 year ago today, this happened. And it was a very special day for us.
And that's 15 seconds and counting.
And here we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. And liftoff. Liftoff. Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
AG2 credits are nominal.
So we were able to, on a Falcon Heavy launch vehicle, launch Europa Clipper again, October 14, 2024, right after an unexpected hurricane hit Florida. And we were able to recover and get Clipper launched on its way to Jupiter. It was a great day for us, a great day for the whole team, everyone that was involved in the project. One more video from that day that's really special to me. And it's an image of the spacecraft
Europa
separating.
Separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon, Europa. And what a sight, Mick.
That is absolutely gorgeous, Gerald, to see Europa Clipper on its way. Successful deployment from stage 2. Falcon Heavy performed very well today. Teams behind us are clapping and enjoying. That is a beautiful picture.
I agree. This is one of the highlights of my career, to be perfectly honest with you. I was able to be at JPL on this day. I was hosting some guests, and we were watching this all happen live. And of course, if you've worked on a mission like this and you're watching it happen, you're pretty nervous, right? Because you're wanting everything to go as smoothly as possible. And on that day, it did. Everything that we wanted to happen happened. And we are able to have Europa Clipper on its way now to Jupiter. So since that, we've had some other events as well. So we have gotten, you saw in that photo our spacecraft, but it looked kind of like a box. But now it looks like it will look when it gets to Europa with these big solar panels that I'll show you later. And we were able to deploy those. We were able to deploy our instruments. And now we're in our final, mostly final configuration. We did what was called the Mars Gravity Assist back in March of this year. And that is really a close contact with Mars. We'll do one with Earth actually in December of next year, and we'll get to Jupiter in April of 2030. I have some cool videos to show you kind of how all of this looks coming up next. So Europa is in this little, the Europa Clipper spacecraft is in this little pink trajectory going here, and you can see the bodies that that we're engaging with. First thing that you will see is us dart past Earth. You saw us dart past Mars, and then you see us go out to meet up with Jupiter in 2030. And so this animation just shows that our mission designers are really good at designing trajectories that allow us to both use the gravity of a planet like Mars or a planet like Earth to help give us an additional boost on our way to Europa. Our Europa Clipper spacecraft. So this is like one of the biggest things that we send into space right now, the NASA SLS rocket. It's taller than the Statue of Liberty, which is about 6 school buses stacked in length. Then we launched on a Falcon Space Heavy, which is about that size. And then you see the Europa Clipper that fits within it. And so about how big is Europa Clipper when those solar arrays are deployed? It's about the size of a basketball court. And so it's a fairly large spacecraft. It is the largest spacecraft that NASA has ever built to send to the outer solar system. Here are some cool images of the spacecraft as it was being assembled and tested at JPL. You can see that this left picture is us going into our thermal vacuum chamber, which allowed us to simulate the thermal environment that we will experience in space, both closer to the sun and really far away from the sun at Jupiter. You also see these what we call blankets, and because it gets very cold out there by Jupiter, we wrap the entire spacecraft in what we call multi-layer insulation, which is really just a blanket to keep the spacecraft from getting too cold, as it is really far away from the sun and having to operate in that very cold extreme. Here are some pictures of that gigantic solar array. You can reference it to the size of an adult male, fully deployed, one wing of it at least fully deployed. So they're quite big. They were quite complicated to handle. They were built in Europe and sent over to the launch site, where we integrated them with the spacecraft right before launch. All right, so you've seen some pictures. Here is kind of a 3D replica of our spacecraft. It has some key features. It has a camera that we use to take pictures of Europa. It has an infrared spectrometer that we can use to take pictures. It's a 3D spectrometer we can use to take pictures in infrared. It has another thermal imager that allows us to look at a different wavelength of infrared. It has a dust analyzer that allows us to kind of sniff particles and understand what they're made of once we are orbiting Europa. We're orbiting Jupiter. We have a mass spectrometer that allows us also to understand what the particles in the environment around Europa are made of. And we have another camera that allows us to image in ultraviolet. These little pointy things are a radar that are sticking out. They operate in 2 different radar bands and allows us to send radar pulses down to the surface of Europa and try to use the information that we get from them to understand what that surface, what's happening below the surface there. And we have 2 instruments that allow us to understand the magnetic environment of Jupiter, around Jupiter and Europa. And that's very important. We could talk about that a little bit more. All right, what happens when we get to Jupiter? So when we get to Jupiter, we do these orbits around Jupiter that get closer and closer and closer towards Jupiter, and then they start to be mostly around the same type of orbit size. But you see, we just completely go into the near Europa, we fly by it, and we come back out. There is a very important reason why we do that, and we don't just orbit Europa and just sit there and take all of our pictures. And it's because I'll show you in a slide later, the environment at Europa is not quite that friendly to spacecraft. It is a highly charged radiation environment that can very quickly damage your spacecraft electronics. So we had to be quite careful how often we went into that region of Jupiter's orbit when we were designing these trajectories, so that we could make sure that we didn't prematurely degrade our capability. So what does that look like? This is a picture here of Europa. Is this little set of ellipses where it shows you intensity wise. Basically, you could just view those as high intense particles, high radiation. And you see the spacecraft just kind of following along, always trying to catch it so that we get right by it, but we don't stay in this high area. So we really had to consider the strong magnetic field of Jupiter when we were designing. And because of that strong field, what tends to happen is every time the spacecraft goes near Europa, we get a little bit more of that radiation dosage. And so it accumulates over time. And there is a maximum amount of radiation a spacecraft can withstand before all of our electronics stop working. So we monitor how much radiation we're accumulating on the spacecraft to understand when we get to that limit. So using the information that we have and everything that we know, we've designed about 50 of what we call these flyby orbits, where we get close to the moon of Europa, and then we try to observe it up close, but then we go back out and come back around again. What this does is it creates this big web of flybys. And these flybys serve a couple of purposes, but they allow us to observe Europa at different longitude and latitudes across its surface, so that we can basically understand it across its entire surface. We are doing that over about 3.5 years of studying the moon. Again, our mission design allows us to minimize our time in that radiation environment. And then we're able to kind of do the same thing kind of over and over again, but looking at a different part of Europa each time. It's a pretty good mission concept. And we're really excited about it. I have a bunch of other slides I could talk to and go into, but I think now would be a great time for me to stop talking, for me to see what types of questions that you may have about the Europa Clipper mission.
Yeah, absolutely. Winston, thank you for that great summary of the mission. I love those video clips of the launch. And then I had no idea that the orbit was going to be that complicated. That many flybys, and just what it takes to keep the spacecraft safe, but then balance that too with getting the pictures and the data and the information that you want to get from that mission. That is, yeah, absolutely wild. Very cool. Those graphics were great. Okay, I'm going to tuck the presentation backstage, so you and I are nice front and center again. And then if you're tuning in with us, send in those questions via the chat sidebar. I can see we've got a good group tuning in with us today. Winston, a lot of our questions are going to come from grade 6 classes, because that is the sweet spot where space is being studied in a lot of elementary classrooms. So I want to start with the first question. This is from a classroom in Toronto, and they would like to know, they watched that video and it made them nervous. So they're wondering how you felt seeing something you worked on for so long sitting on top of a bunch of rocket fuel about to go into space.
I would say me personally, I was a nervous wreck. I could not sleep the night before. I was excited. I was, and so it was just so many emotions. I would say my colleagues similarly felt the same, where many of us had like really important jobs to do that day to make sure that, everything that we wanted to happen would happen safely. And so most of us would, I think, describe it as a mixture of extreme nervousness and excitement, right? It was both. And it was probably one of the highlights of all of our careers.
All right. And so we saw the video too of, it was obviously folded up inside the top of the rocket. It had to deploy those huge solar arrays. How long did that process take?
The solar array deployment was actually, it took only a few hours. It wasn't that long. Of course, we couldn't see it happen. It would have been wonderful if we could see it all happen. But shortly after we separated, in that video you saw, one of the first things that happened is we deploy the solar arrays so that we can start to get power positive, is what we call it, where the arrays are on the sun and starting to charge our battery.
Okay. So this next question here, this is from a grade 6 class, but this time they're out on the West Coast. They're in British Columbia, and they're curious about, you touched on the gravity assists. And so they're saying they thought gravity pulls things towards a planet. So how are you using gravity to push things away, I guess?
That's actually a great question. So what happens is gravity does do that. When you go into, orbit, it will pull you, into the orbit of a planet. But the other thing it does is when you're coming at a body that has a gravitational force as fast as you are, right? There is now competing forces because you have your momentum from your velocity, and then you have that gravitational pull. So what it actually does is it accelerates you first. Before it catches you in its gravitational orbit, it accelerates you along the orbit. And so what we do is we just allow it to accelerate us, and then we use our own propulsion to kind of scoot on out before we get stuck. So yeah, that was a great question.
All right. Very cool. I love the way you describe that as well. Very cool. Okay, let's see what else we have in the chat here. All right. We've got some grade 8s in Illinois. And they're curious about, it's been a little bit since it launched, Europa. Has there been any bugs or any technical details that you, the team, the engineers have had to work on?
No, everything's been perfect. No, I would. That never happens, actually. So I would say we have been fortunate so far to not have any real major anomalies as a system. Things have gone, quite frankly, everything has exceeded the expectations of the team. We have surprised ourselves at how few problems we have experienced. That being said, minor things always do happen, and it's early in a spacecraft's life and it's in its environment. So we are learning things that we may not have appreciated prior to launching. But those things have all been minor, and everything that we've set out to accomplish so far, we've been able to accomplish.
All right. Well, that is good news.
Yeah.
Yeah, because obviously it's complicated to do. But what always impresses me is, even thinking of projects like Voyager that have been going for like 40 plus years, and still they're, scientists, engineers are putting their heads together and solving problems and restarting systems. And it's amazing what we can do from Earth with spacecraft so far away. And that brings me to the next question here in the chat from some fourth graders. How long does it take for Europa, once it's orbiting, to send information back to Earth? How long is that?
Man, that is a great question, and I wish I was better prepared for. So as we get further and further away, that time increases. And so at Europa, I think the worst case is probably around what we call 10 minutes of one-way light time. And so that means from the time it leaves the spacecraft, it'll take about 10 minutes, either way, from the time it leaves a ground station or the time it should take about 10 minutes to get to where it needs to go. And that's just one-way light time. It also depends on our antenna strength, right? Like how much strength we have in our antenna at any given time. Yeah. How much data we can send across that link in that amount of time. So sometimes it's 10 minutes, but it's also like very small amounts of data, and then sometimes it's 10 minutes and it's a larger volume.
Yeah. All right. This is the same classroom, and their follow-up is about the asteroid belt. Is there any worry about passing through or close to that to get to Jupiter?
No, we deliberately picked our trajectory to make sure that Europa Clipper will, as safely as possible, get to Jupiter with minimal interference. So we, except for those close passes of Mars and Earth that we're going to do, we don't expect there to be any significant other encounters, right? We don't want to encounter anything else.
Yeah. And I think there's more space out there than students think. I think when you see movies and it's like everything's so crammed and close together, I don't think it's quite like that. Not that dramatic.
Right.
All right. Okay. Going back to the chat here. This is one of our favorite questions, Winston, that we get from classrooms. This is sixth graders again. These ones are in Manitoba. And they're wondering, what inspired you? What led you to pursue a career in space exploration?
So that's a great question. I can say that when I first started as a student in engineering, I didn't think too much about space, honestly. I started out in civil engineering, and then I went into more mechanical engineering kind of research and development. And so I always thought I would work on something more terrestrial, like medical devices or, you know, bridges or something engineering that is more for like the everyday human experience. It wasn't until I was an engineer at Northrop Grumman that I had the opportunity to work on a space project. And I was completely fascinated with the work, right? It just consumed me. It was interesting. It was hard. I felt challenged. I felt like these were problems that I wanted to solve. And I think it was really then, and that was probably about 4 years into my career that I really kind of the light bulb switched, and I was like, this is what I want to do. And so ever since then, I've been really enthusiastic about working on space and kind of, you know, a little bit of a elitist about it. It's like now I can't envision working on anything that's not space. And so, yeah, that's when that light bulb and that passion clicked for me. And that was probably around 2011.
All right. This question here in the chat was inevitable. I knew it would come up, this next one. You know, we think about Mars. There was a really cool sample that's on Perseverance right now that we think could be a biosignature, but you know, we hope there can be a Mars sample return mission to get that sample back so we can maybe find out for sure. We think that maybe one of the moons out there, like Europa, with an ocean could potentially be a spot where there might be life. So in your opinion, do you think we are alone in our solar system or galaxy or universe?
My opinion, that's tough. There are plenty of astrobiologists whose opinions I would listen to more than mine, but I'll say for me, I don't know, right? I think one of the things that we like to caution when we talk about life is there's a tendency of us to think about life, other places, as life that either looks like us or is sentient in a way that looks like the things we see on TV when we think about aliens. And I think what most scientists would caution you that study planetary science is that if we were to find life, it would probably look like the primitive life that existed on Earth when Earth was first formed, right? It would look like the type of small microbes that you would find at the bottom of an ocean. It would look more like that, right? Things that are alive, but not very evolved. That's the most likely thing that we would expect to find at a place like Europa. Is there life that could be beyond that? The universe is gigantic, right? So the notion that we are somehow uniquely special in the universe, to me, seems not probable, right?
Yeah, I can't look at the night sky. I can't think of those billions of galaxies with billions of stars in each one and so many planets. I find, for me, it's hard to believe that life only in this one tiny little corner of the universe. So I'm sure whether it is very simple life or whatnot, I feel strongly that there's probably other life out there, which I think is pretty cool. And I can't wait to see what happens with the Mars mission in particular in the future. Now,
yeah, that study, by the way, was pretty groundbreaking. I worked on Mars 2020 as well on the payload team, and that study was put together by a bunch of scientists that we work very closely with. What they found there is pretty groundbreaking in terms of Mars research, right? That was big.
Yeah. From the most recent article I read, and I did an interview with one of the scientists on the team, is it's so tantalizing, this evidence that if we saw it on Earth, we'd be like, oh yeah, that's a biosignature. So yeah, I really hope that we get that answer. I think that'd be pretty cool. Winston, I love this question here. If you, this is from a 5th grade class, and they're wondering if money wasn't an issue and you had an engineering dream team, what would the perfect space mission be for you? What would you like to plan and launch?
I'm super excited about this question. The reason why is I am fascinated with Saturn, and I love Saturn and Saturn's moon. Saturn's moons are very interesting. So for me, working on something going to Saturn would be pretty awesome, especially if it was going to study, a moon. I think NASA has a mission going to Saturn's moon Titan called Dragonfly, and I think that mission is like extremely cool and extremely exciting. And I get to work pretty closely with the principal investigator of that mission and some of the team members. It is a really exciting one. Another one I'm really excited about, which is hard for me to say my dream ones, but all of my dream ones would be to the kind of icy moons of the outer solar system. So Uranus has a study that is ongoing where we want to send a probe there to orbit and land. And I think that's like a phenomenal concept. So I hope that in the future that gets funded as well. So it's really Uranus, Saturn, those outer big gassy planets that we don't know a lot about is what I'd be interested in.
All right. And Winston, I noticed in the chat that you just wanted to update the worst case data return time from Jupiter.
Yes. Sorry. I am so focused on cruise right now that I'm giving you numbers from much closer in the solar system. So the worst case is 52 minutes. I'm now reminded of that because I haven't thought about Jupiter in a while, actually. And so, yeah, it takes about 52 minutes to get data back. In the worst case, there are some geometries where that's more favorable, but the worst case is 52 minutes.
All right. I don't think anybody is going to hold that against you, Winston. There's a lot of numbers in your head, a lot of projects like we listed at the beginning. And in fact, that's my next question from the fourth graders in Florida is I mentioned that you're also on the Venus, the VERITAS team, and they're wondering what that project's all about.
Oh, man. Okay. VERITAS is a mission to Venus to study Venus's surface. And the last real spacecraft that went to Venus to explore it was Magellan, and that was a while ago. So for both of these missions, Clipper and VERITAS, we're sending things to places where it's been like decades since we've had, any data coming from these planetary bodies. And so this spacecraft will go to Venus, study its surface. It's a smaller mission, way smaller than Europa Clipper. It has a couple of instruments, and they're really just going to try to pierce through that thick atmosphere of Venus, which makes it difficult to look at and understand what's happening on Venus's surface. Venus has a very interesting, very active surface. Lots of volcanoes, lots of plate tectonics, things are moving around. And scientists want to know why is that happening? What's going on there? So,
okay. The instruments on Europa, there's some curiosity around, will they be able to see through the ice to map or look at the ocean beneath in any way?
Yeah, that's a great question. So the instrument that can pierce through the ice is the radar, and of course you can imagine that an RF signal can go through a surface, right, and tell you something. The cameras obviously will reflect back off of that brightness, and you can see Europa's surface brightness. It's very bright, right? So off the brightness of Europa, the cameras will reflect back all light. So they'll only be really studying what's happening on the surface, but the radar is what's really going to tell us what's happening at the inside of the atmosphere. And the way radar do that is this kind of technique called interferometry, which I won't go into, but what it effectively means is I'm going to send a signal somewhere, it's going to hit something, and then it's going to come back. And so what would happen is if it hit the ice and it went through, it's designed to go through the ice, but the minute it gets to water, it's going to reflect because it's like, oh wait, this isn't ice anymore, this is something else. So it's really designed to tell us kind of what the thickness of the ice shell in the ocean might be.
All right. Well, I have seen some concept missions. I know they're really just ideas. We're not there yet, but some concept missions of possibly drilling through and putting something into the water. That is pretty wild future stuff. That would be pretty cool if missions like that were possible in the future. Okay, so a couple more before we wrap up. We're getting close to our time for today, but I'm loving the chat today. I'm loving all the great questions that are coming into classrooms. So thank you so much for sending those questions. And to those who will tune into the recording later, thanks so much for tuning in with us. And yeah, it's always great to be able to do some space exploration with your classrooms. So Winston, what is we have had a few different engineering projects. We know Voyager's lasted way longer than it was supposed to. A Curiosity on Mars, again, way longer. We talked to one of the pilots of the Ingenuity helicopter, supposed to be 5 flights. They did 72. So is there a hope or a belief that you guys just really engineered Europa and it's going to do even more than you're expecting or planning?
Oh, absolutely. We always hope for what we call an extended mission, and if it is the case that we're still going at the end of those 50 flybys, we would try to do as many more as we could. It makes it's a little bit harder to do extended missions for orbiting missions, especially deep space, because you have to always prove that you can safely kind of dispose of the spacecraft. We wouldn't want for something bad to happen, right? And then we crash into Europa and contaminate it for future study. So so our burden is a little bit harder than like the Mars missions that get to just kind of drive on the surface until they stop working. We have to actually prove that we can safely turn ourselves off. Yeah. So we will do as many flybys as we can before we're unable to keep going.
All right, very cool. Okay, let's see. I think we can grab one more here from the chat. Let's do. Okay. So with this mission, with the solar rays, the panels, how much energy are they able to get from the sun as far away as Jupiter? I'm trying to think of the best way to ask that question.
I'm trying to figure out the best way to answer it without giving you a number that will inevitably be wrong. So
is that why they're so big?
Yeah. They're made to be very, very big to support our. I mean, we have. I think I showed you we have like 10 instruments that operate all at the same time. We have we're the largest spacecraft, so we have to have those gigantic solar rays because we do need quite a bit of energy, and so that's why they're so gigantic. I can't remember off the top of my head how many thousands of watts and watt hours it generates, but it is a lot. They're big so that they can generate a lot of power.
Yeah. Well, at least you don't have to worry about the dust like on Mars with the rovers. Yeah. So you don't have to worry about the dust and dust storms covering those.
We just have to worry about the fact that the sun is very far away.
Yeah. Well, we've definitely seen those pictures. Like the Cassini when it took the picture of the little dot of Earth. And then, of course, the sun's going to show up a little bit bigger, but it's still pretty darn far away. Winston, this was such a pleasure. This is the first time we've had you join us. I want to start off with a huge shout out to our classrooms. We love the questions. Thank you so much for joining us and sending in all those great questions today. And Winston, it was great to have you with us and that update on Europa. It is exciting times. There's missions all over the place right now.
Yeah, and if I can, before I go, Joe, I would like to say that for all of you who find space interesting and you love the work that you see presented about the helicopters, about Mars, about Europa, VERITAS, there is an opportunity for you to help advocate to NASA, to the federal government about the importance of these programs to you. There are some resources I can share with Joe. He can put up. There are places you can go where even as students, you can say, hey, this is important to us. Please keep providing the funds for us to do this type of work. I think we're at a point where that's very important for everyday people not working in space to kind of speak up and say that you want to keep seeing, the federal government invest in this type of science.
Yes, absolutely. Winston, send me those links. I'll make sure I put that out in our next newsletter to our classroom community as well. And I couldn't agree with you more. There's so many important technologies that we use here on Earth thanks to space exploration. We can understand our planet so much better. The benefits are huge. Just curiosity, learning more about how the solar system formed and our planets. And there's the reasons just go on and on and on why space exploration is so important and why we need to keep funding these incredible missions to explore more of our solar system.
Yeah. Thank you, Joe.
All right. Well, I hope everyone has a great weekend. We hope to see you in lots more of our events in October and, of course, throughout the rest of the school year. But for now, we're going to sign off. Thanks so much for hanging out with us, everybody. Thanks, Winston.
Thank you.